new stuff. So what we're going to be looking at now is a new structure, our aromatic structures. And we've kind of encountered these periodically throughout the semester. And we kind of said, oh, okay, well, don't worry about those. Just realize that they don't react like the way we would normally expect a double bond to react. So before we get into looking at those reactions, we need to do a quick review of our nomenclature. Everybody seems to have some issues dealing with nomenclature. Go back through and review the rules. All it is a rule. You have to know the rules. If you memorize everything on this slide, you're probably set as far as anything that can get thrown at you. This does skip over stereochemistry, but it covers most of the basics. Okay? If we look at our primary category through that center, you'll notice that when we look at all of those functional groups, they don't make any mention to aromatic structures. And that's because we don't really look at aromatic structures as a true functional group. Okay? They get referenced kind of secondarily. And that's largely because they are incredibly stable, which means they don't react the way we would typically expect them to. And in most circumstances, they don't react at all. Okay? So we tend to ignore them as a functional group. That said, we still have to come up with some way to name them. So if you take a look in the lower right-hand corner, we've got two structures that we can go through and name. Okay, and this is where the nomenclature within this system is kind of nice. Okay, our longest chain in this case we will name as our aromatic ring, which in this case is just benzene. Most of the aromatic structures that we will deal with for the rest of the semester are benzene-based. When it comes to nomenclature, it is strictly benzene, so you don't need to worry about the other aromatics. So what functional group do you see on both of those structures, or on either of those structures? Do they have any substituents? There's a chlorine. How do we name chlorine as a substituent? Chloro. And we name the rest of the structure benzene. So guess what the name is? Chlorobenzene. Nice and straightforward. Okay. And the next one down.
Nitro?
Okay. That is the nitro functional group. And because we'll keep coming back to its importance in chemistry. So let's go ahead and write that out real quickly. Your nitro functional group will almost always get abbreviated as NO2. But you need to remember its overall chemistry within that structure. And then we've got our benzene ring. Why is it important to remember that Lewis structure for our nitro functional group? Resonance is an important answer in this. In what respect?
Well, we have the positive nitrogen and the negative oxygen.
The negative oxygen does resonance with that nitrogen, pushing the electrons back out the other side, meaning the oxygens never really hold a formal negative charge, right? Which means they aren't nucleophiles, and they aren't bases. That nitro functional group, due to all that charge, and particularly a positive charge on an atom that does not want to hold that charge, means that the reactivity in that functional group is virtually nil. Okay? So they are, for all intents and purposes, neutral. So that is one important aspect on addressing the nitro group. The other important aspect has to do with resonance the other direction. What would the resonance with the ring have to do? And notice that I said with and not into, as you just put out there. Can I do resonance into the ring from the nitro group? No. Okay. The positive charge on that nitrogen means that there are no electrons on the nitrogen, which means it cannot donate electrons to the ring. Instead, what ends up happening? The ring donates electrons out towards the nitrogen, which means what charge builds on the ring? A formal positive charge builds in the ring. Okay? Very, very important distinction and identification to go through and make when you look at that structure. Okay? Back to our nomenclature. We said that was a nitro. The rest of the structure is named benzene, and so we have nitrobenzene. Very creative, very simple. The next big thing that pops up is that you'll encounter common names for a lot of benzene derivatives. Okay? Tons of different benzene derivatives, so you're going to have to be aware of some of those common names. You've seen a lot of these before, or at least some of these before. Before we start looking at those, I realized that I missed a slide referencing the locations on the aromatic ring. So let's take a look at it. I'm going to put X. What does X represent in this case? All it's representing is something. Okay? And in particular, it's going to be my frame of reference for the other positions on the ring. Okay, so that X can apply to anything that I possibly want. The very next position on the ring, 2 atom X, whatever that atom is, can sometimes be referred to by multiple names. What might be one name that you've heard of already? Okay, I would argue you haven't heard of ortho, but you may, since you said it, you very clearly have. Could go with alpha. That's not a bad idea. Okay, I would argue there's another one. 2. Okay, this is X is at position 1, which means that next position is 2. And the next position, 3, 4, 5, and 6. When would we use the numbering nomenclature system? With our standard naming system, which you're responsible for acknowledging and recognizing as the IUPAC nomenclature system. That is the one that you are responsible for, which means you need to be able to reference the individual positions on that ring based on the number. That's what you're responsible for. This extra term of ortho is not officially IUPAC. It is a common name application that allows us to reference that position relatively quickly and easily with a name as opposed to a number. Okay, that is the only reason we use it. That said, as fun as it is or as simple as it is to go through and come up with a name, that is of course way too much writing, and we instead refer to it as the O position. Okay. Position number 3. Different chemistry. Gets referred to by a name. Meta. Which again, too many letters. L, right? M, because that meta begins with M. Next position. Position 4 will get referred to as para, or the P position. Okay. These are used very similarly to the not EZ notation, the cis-trans notation that we've seen before with double bonds. It gives us the relative location of any 2 groups. The key piece being 2 groups. Okay. 2 groups on a ring can be ortho, meta, or para. Does that mean those are the only 2 things on the ring? No, we can have a bunch of other stuff there. Okay, but what we are referencing is those 2 individual pieces. We now have a way to reference their locations. You'll notice I did not label 5 and 6. I might have a guess coming out of the color coding. They're just meta and ortho. So this is one of the advantages behind naming these positions. Why are 2 and 6 named the same thing? They are, for all intents and purposes, the same thing. They have the same arrangement with respect to every other atom in the structure. Because remember, you can flip the structure over. So for all intents and purposes, 2 and 6 are chemically identical. 3 and 5 are chemically identical. Okay? Kind of makes sense? So we will make reference to these locations throughout the rest of this section. After that, our common names. If we go through and change our substituents, we may reference the new compound according to a new common name. You've seen phenol before. Okay? Phenol had its own name primarily because it had its own chemistry. Okay? It was more acidic than an alcohol, but it wasn't a carboxylic acid, so we ended up naming it a phenol. The rest of those on that list you probably aren't aware of, at least not yet. Okay? You are technically responsible for these. They kind of pop up, kind of not. So just be aware, watch out for them. When it comes to nomenclature, you may see reference to these individual common names. You aren't strictly responsible for them because these are common names and you're responsible for IUPAC. Okay? So watch out for them when they do show up. Just as a fun little test here, TNT. What is TNT? Trinitrotoluene. So if we went to the structure, what would our structure look like? So our structure of toluene, good job. And now you said 3 nitros. Where do I put those 3 nitros?
They're at 2, 4, and 6.
Okay, how do you know they're at 2, 4, and 6?
Because that's what TNT is.
TNT doesn't have the locations of those nitros specified. TNT is actually 2, 4, and 6. Trinitrotoluene. We put our nitros here. Figuring out why they are at those positions, we'll actually discover a little bit later on when we understand the chemistry of how we can put those nitro groups onto the structure. Ends up being an incredibly dangerous reaction because it's TNT. Okay? And in the process of making it, you end up having to use concentrated acids and high heat, both of which tend to cause explosives to explode. So in the process of synthesizing it, you run the risk of it actually exploding in not particularly safe conditions. Okay? After that, we've got the spectroscopy of your aromatic compounds. Here we've got this big long list of signals for which spectroscopy? This is your IR spectroscopy, and for your aromatic compounds, which you're referencing now. Not that big of a deal to go through and reference. The key things that you will zero in on, or what you should be zeroing in on, we've already talked about throughout the course of the semester, would be your CHSP2s. Okay. The rest of it, I would argue, is not worth the effort. Okay. If you know that you have an aromatic compound or have a very strong inclination that that is what is present, then you can go through and evaluate the rest of those signals. But it involves a lot more effort and a lot more memorization to go through and process those. Okay? Some of those signals can show up in the fingerprint region, which can be useful. So again, this is something that when I went through and did IR spectroscopy, I didn't trust that they said just do the functional groups, and I went through and tried to learn as much as I could out of the IR spectra. That was before I learned that HNMR was so much more useful. So I spent all this time memorizing and figuring out how to interpret IR to only find out 2 or 3 weeks later that all my effort was a waste of time. Okay? That waste of time looked at the 900 to 700 region. And by looking at the intensity of the signal, you can then determine something about the substitution pattern of your aromatic ring. So if we pick our classic substitution pattern for aromatic rings, the para substitution, what this is referencing is that if I had an aromatic ring with para substitution in the roughly 700 to 800 region, I would expect to see a strong signal. What's the issue with the fingerprint region? There's a lot of stuff there. So I may very well be seeing a strong signal due to something else entirely. Okay? So it's something that you need to use the grain of salt. It can be very helpful. And in fact, when it comes to our lab that we'll be doing next week, I do kind of expect you to at least look at this and see if you can pull some useful information out of it. Okay, you may very well find that you can't. That's okay. The other region that you could reference for your aromatics, you'll notice, is not in the fingerprint region. 2000 to 1667. Fun part about that region is because it's not in the fingerprint, you are now officially responsible for it. How many of you have looked in that range and interpreted anything about your aromatic rings? About your aromatic rings. Looked in that range. Probably not about aromatic rings. These signals tend to be very, very, very weak. Okay? But if you go through and look at the patterns, you'll notice that each of these patterns are slightly different for each of those substitutions. So you can use this information to predict something about the structure of your aromatic compound. It tends to be so weak as to be not useful. Further, if we threw in a carbonyl, remember your carbon-oxygen double bond? What is that going to do to this region? What's that? It's not going to make it smaller. Where's the carbon-oxygen double bond show up in IR? 1700, which is right in the middle of that region. And the 16, or your carbonyl peak, your carbon-oxygen double bond, is how intense? Super intense. What is it going to end up doing to all of this aromatic information? It's pretty much going to hide it. Okay, so if there's a carbonyl, you tend to wash that signal out, or wash these signals out and you can't interpret it. Okay? So it's kind of spotty. If you've got access to it, you can use it. If you don't have access, don't worry about it. Last one, when we looked at our ortho positions, we said they were symmetric, right? The 2 and 6 position were identical as far as chemistry goes. Where would we use that useful, or use that symmetry to benefit us? We can use it to determine how many unique hydrogens are in our structure. So if we had a monosubstituted benzene, how many signals would we expect in our HNMR? 3. Okay. Our ortho positions would show up as 1, our meta positions would show up as 1, and our para, would show up as another 1. Okay? If we take that a step further, what can you tell me about the ortho position? How many neighbors do they have? 1. Why do we not look at the other half? I mean, there is a neighbor there, but isn't there a neighbor over there? Doesn't that make 2? They're identical. They're chemically identical on both ends, so we don't reference that. We only see it as one neighbor, which means how many peaks would I expect?
2.
We said 1 neighbor, which means 2 peaks, also known as doublet. Okay. What happens with the meta position? It's going to have 2 neighbors. We've got our hydrogen at our ortho position. We have our hydrogen at our para, which means 2 neighbors, 3 peaks, and we have a triplet. Our para position, two neighbors. In the case for our ortho, it was only 1 neighbor. Why did we not count the left side? Those hydrogens were identical to each other. Okay? Not the neighboring hydrogens. We weren't referencing those. We were referencing the original hydrogen that was our source. Those hydrogens were identical. So when we move to the para position, there are 2 hydrogen neighbors, which then means 3 peaks, and again, a triplet. This kind of processing should happen very, very fast. What this slide is attempting to show is a quick summary of a whole bunch of different substitution patterns for aromatic rings. Because if you then recognize what those substitution patterns are, you can predict, like we just did, for a monosubstituted structure, what signals you would expect to see. Once you have that information, you can look at your spectra and say, ah, that matches what I said was the para-substitution. So that means whatever my answer is para-substituted. Okay? It's that quick processing that'll help you out by looking at and identifying those signals. Is it as simple as what's shown up here? Not necessarily, because what we've got shown is they're showing some where it's the same, some where it's different, which means we'll end up with all sorts of different substitution patterns coming out of this, which means we end up with different signal collections. As a general rule of thumb, the favorite for standardized tests happens to be the para-substitution for two unequal substituents. What does that generate? What hydrogen is unique to that blue hydrogen? Is there any hydrogen just like it? The one right below it on the opposite side. How about at position 3? Same deal. So there are two sets of peaks for our hydrogen NMR. What other information can you look at? Go ahead, I think you said it. Doublets. This is often referred to as a doublet and a doublet. Sometimes you'll hear it referenced as a doublet of doublets. That is wrong. A doublet of doublets is complex splitting. That's splitting of splitting. This is not splitting of splitting. Okay, this is two signals. It is two doublets. So if you look within your aromatic region for your HNMR and you see two sets of two peaks, what you should be referencing in your possible answers would be the para-substitution. Kind of make sense? Okay. I kind of jumped the gun. Oh, no, I didn't. Okay. You can also go through and do it for carbon NMR. As you can already tell, my preference is for HNMR. That's typically what you're responsible for seeing anyway. Questions on your spectroscopy? Okay. So why look at benzene? We've seen this before. What are we referencing in this case? What type of reaction is occurring? Where are our reactants? Where are our products? We've got our reactants running across the top, and we've got our product down below. We're taking our reactants, we are reacting it with hydrogen, so we can reference it as a hydrogenation reaction. Okay. In the course of that hydrogenation, we can then reference the energy associated with that reaction. When we hydrogenate a single double bond, it releases 120 kilojoules per mole. Why would it release energy? Pi bonds are higher in energy than sigma bonds. So when we react with hydrogen and remove the pi bond, we are releasing that energy because we're now going to a lower energy state. If I add a second pi bond, that means my energy should go up because I have, again, a higher energy functional group. If I add a third pi bond, the energy should again go up to a higher energy state. Each time we go up to a higher energy state. And we could now predict something about the energy released in the course of that reaction. Okay? That's all we're trying to see here. And it steps relatively close to evenly all the way up. Two double bonds is roughly double one single bond, or one double bond. Okay? Why benzene becomes interesting or fascinating is that if we actually look at the energy associated with hydrogenation, it is not 360 kilojoules. It is 208 kilojoules. It was actually lower than we would expect, which in and of itself isn't that big of a deal, but not only is it lower than what we would expect, it's lower than if we had only 2 double bonds. What does that mean is happening within our aromatic structure, or our benzene? Heard somebody mumble it.
It's stable.
It's stable. There is something about the arrangement of the electrons and the atoms in a benzene structure that it is incredibly stable. As soon as we hit 20%, I'm going to start walking. Okay? So that's bizarre. There's some extra feature happening here. Okay? Well, the extra benefit that we get within the benzene compound is that it is a fully conjugated structure, meaning the double bonds alternate. And it is cyclic. So something about a fully conjugated cyclic compound causes this massive drop in energy, and our molecule becomes much, much more stable. That is kind of an interesting phenomenon. As soon as we find that, of course, what do we then want to do? See if we can find other molecules. So it turns out that we were able to find other molecules. Okay? The cyclopropenyl cation, shown on the right, is also equally stable. If we take benzene, lots of double bonds, we would expect maybe a Diels-Alder reaction where we react to double bonds. We would expect an addition reaction where we add bromine. Okay? Benzene did nothing of those two reactions. If we take the cyclopropenyl cation, same deal. No reaction occurs. So this isn't something that's confined to just benzene. Other structures also go through and do this. Okay? Anybody notice any patterns between those two where you would say, that's why it didn't work for cyclopropenyl cation? If we take a look at the pi electrons, okay, we have an odd number of pi bonds. That's an interesting observation. That's true. What else is true? Big conclusion was fully conjugated cyclic compound. What did you say? They're both rings. Okay. And for the cyclopropenyl, we might even expect that to be more reactive because it's in a very small ring. It ends up being the same lack of reactivity. Okay. So we now have a ring for both of these. We have an odd number of pi electrons, or pi bonds. What's the other important aspect from that previous slide? Fully conjugated. It has to be the cyclopropenyl cation. Why is that important? What is the hybridization of that carbon? sp2. Which means it has an empty p orbital which can conjugate with the rest of the structure. I can do resonance around that ring. Okay. So this resonance ability seems to be a large contributing factor to this. So if we take a look at a couple other examples. Cyclobutadiene, would I get resonance for this guy? Yeah, those are resonance structures of each other. Could I do resonance with the other one? Yeah, resonance seems legitimate there. Both of these rings, all of these have a p orbital on which to pass electrons through. So we might predict for both of these that we get that same stability. Okay, but Jimmy pointed out an interesting feature. We said odd pi bonds in our first two cases. Do we have odd pi bonds in these two molecules? No. What ends up happening? In that first case, what type of reaction did we do? It's a Diels-Alder reaction. Maybe a bit difficult to see. It's because it's not one Diels-Alder reaction. It's two Diels-Alder reactions. And the one below, what happened? Just a standard addition reaction. So resonance is clearly something that increases the stability or makes something more stable. Okay, but it's not the only thing. There's something else going on in here that for some reason, in the case of benzene and our cyclopropenyl cation, make them unreactive to Diels-Alder reactions, make them unreactive to addition, but somehow when we scale up to these other ones, we have this increase in reactivity. Okay. Someone went through and summarized our rules on this. Okay. And it gets to what Jimmy was referencing, the number of pi bonds. To be an aromatic compound, to have the stability of a benzene ring, we must be a fully conjugated ring with overlapping p orbitals. Okay. Some of these become more important than others. That overlapping p orbitals, okay, that is technically not valid. Whoops, dang it, I knew that was going to happen. For this structure, those p orbitals do not overlap. How do we know that? Good question. It's really hard to see. Okay, really the only way you'd be able to see it is if you built the model to see that that structure actually bends. The next big thing that comes out of this, making this observation was done by a particular person because they've put together this observation and we saw things that now don't react and now looked at things that did react. We, of course, name it after them. We get Huckel's rule. We're looking at an odd number of electron pairs. Okay. This becomes an interesting issue when we go through to assign these. Your rule is officially 4n plus 2 to get your total number of pi electrons. N can be anything. When we look at benzene, what is N? It's kind of a challenging question. 4n plus 2 equals our total pi electrons. What is the total pi electrons in benzene? There are 6 pi electrons. 1 or 2 from each of those pi bonds. What is N? 1. Okay. What does that 1 have to do with anything? It matches the formula. Don't take more meaning out of it. That is it. What is N for the cyclopropenyl cation? 0. Okay. It fits the formula. That's all we're looking for. Okay. Another way to go through and do this, because some students don't like dealing with that formula. What numbers of electrons satisfy our aromaticity rule? Well, 2 works. That was n equals 0. What happens if n equals 1? 6. N equals 2. N equals 3. 14. What's our relationship between each of these? Add 4. That works pretty well. We can continue to go on and on and on with this. Okay? And it could go on infinitely. Are we going to predict anything out beyond 18? That is perfectly valid. Why are you shaking your head as 18? Why do we tend to not worry about that? It gets too big. Remember, I have to draw the structure. If I have to draw it so that you answer the question, I'm going to work probably down in that 10, 6, and 2 range. A lot easier for me to go through and draw. And you may think that I'm just lazy. Everybody's lazy. Okay? It's not just me. Very rarely will you see a question up at 14. I've never seen a question up in the 18 range. Okay? So you can remember 2, 6, 10 as your number of pi electrons. Okay? Questions? Okay, so those are the rules, but why? Why does that matter? Okay. Well, if we go back and reference chapter 14, 14 where this came from, remember we talked about molecular orbital theory. Well, molecular orbital theory is what's used to say why for each of these things. If we take a look at the structure for cyclobutadiene, okay, what we've got drawn here is what? Any ideas? Highest, lowest, middle energy? Okay, a lot of people are saying lowest. Sorry. It is the lowest. How do you know it's the lowest? They're all the same shading. Okay? Which means all of those orbitals are overlapping, which means we have the lowest energy conformation. This ends up being the lowest form on our energy diagram, our lowest molecular orbital. We can go through and look at all the other possible ways that we could change the orientation of those orbitals to see how they overlap, and what you will end up finding is you will generate the image shown. There are 4 molecular orbitals for cyclobutadiene. 1 incredibly low, 1 incredibly high, and then 2 of equal energy in between. If we go through and do this for cyclohexatriene, also known as benzene, we'll get the energy diagram shown. 6 molecular orbitals. Why is this important to understanding aromaticity and what's going on within this? How many electrons go into cyclobutadiene? We can draw the structure real quickly. How many pi electrons go into cyclobutadiene? There are 4 pi electrons. Where should that first pi electron go? The bottom? I don't quite like bottom. Give me a little more detail on that. The lowest energy. Our lowest energy orbital needs to be where our electron goes. Let's put the first one there. Where's the next one go? Still lowest energy. Where's the next one go? Lowest energy, I only have one out. Next one? So there are 2 spots now. Here or here. Where should I put that next electron? I'm hearing one on the right. I think you may have said it scientifically, so maybe I want to hear what you say.
Oh, I was just going one on the right because it's the, you have to fill up the orbitals before you fill up the different orbitals before you start putting 2 in.
Half-fill orbitals before you double up, which was Pauli exclusion, right?
There was some rule for it, and I forget what
There's some name on that rule. But we have to put our half-filled electron first. So we end up, it is Pauli? That's good. We got 3 people saying that, so let's just agree with it. Leave it for the internet to make fun of later. Okay. How many pi electrons go into benzene? I don't accept a lot. Okay. We've got 6. So if we start putting our electrons for benzene, where do we go? Lowest. Next one. Next one. Next one. I'm going to go back on the right. Does it matter? No. Okay. Good shrug. And then the last one. Why is benzene so much lower in energy than cyclobutadiene? What is different about its molecular orbital picture from cyclobutadiene? All of the orbitals that have electrons are fully filled. Okay. How many electrons can be put into benzene? At this point, none, unless we move to a higher energy. We'll reference that higher energy in a second. In the case of cyclobutadiene, I've got 2 slots where I can slide electrons that are already occupied. Okay. That makes cyclobutadiene much more reactive, because what I effectively have is a diradical species. That diradical reactivity makes it much more reactive than benzene. We expect it to go through and react. Benzene, on the other hand, we don't see that reaction. Okay. So it's coming out of understanding the molecular orbital diagram and where those are coming from. How did we go through and draw each of these energy diagrams? How did we predict how many molecular orbitals to have? How did we do it with, say, just butadiene? clear everything and just draw out that structure real quickly, because this is one I would expect you to be able to do relatively quickly. Say on like the first test you guys had. What was that? We also have 4 molecular orbitals. How did we decide that? What does the next one look like? What's that? One node. How do we know what the next one looks like? 2 nodes. Is that one right? And 3 nodes, and so on. So how did we get our molecular orbital diagram? We looked at how our orbitals overlapped and did all those predictions to draw those out. What happens when we switch to a cyclic structure? Anybody see how that might be a little bit more difficult to go through and do? Okay, how many of you want to do that? Let's try that. Okay, you're saying no. I agree with that. It's a good idea. We want a simpler method to do this. Someone went through and noticed by drawing out the molecular orbital diagrams using this overlap method multiple times and noticed a particular pattern fell out of it. Okay. That pattern or that style was named after them. We can look at what's known as a frost circle. Draw a circle. Whatever your structure is, whatever compound you're trying to decide for your cyclic aromatic compound, inscribe that shape inside the circle where the point is down. Okay, any one of the points, straight down. Why? There will only be one molecular orbital where they all overlap. There's only one possibility. So there's only one lowest energy structure, or lowest energy molecular orbital. Each of those points on your polygon are now molecular orbitals. And you have the molecular orbital diagram. Okay. It's kind of handy. Let's go back and look at what we just had. Cyclobutadiene was a square. If we inscribe it, benzene works out. Okay. Kind of a neat little observation. Connect the dots, if you will. Okay. This allows us to look at the molecular orbital diagram. That allows us to then look at the electrons within those systems, and we can start to predict something about their reactivity. If they are all paired, what does that mean? We have an incredibly stable structure that is typically assigned what nomenclature? Begins with an A. Rhymes with automatic. Aromatic. We have an aromatic structure. What if it appears to match all of those rules except we have unpaired electrons? Well, then it's not aromatic, right? As simple as that. Okay? But it matched some of the rules. Because if I had gone through and, say, drawn, let's just say cyclohexane. Cyclohexane has no pi electrons whatsoever. Okay. If I'm going to call cyclobutadiene non-aromatic, what would I call cyclohexane? Not aromatic. Oh, you're going to classify them as the same thing. That's not a bad idea. Okay. Except the reactivity of the cyclobutadiene is a little bit more reactive than our cyclohexane. Okay, we could even drop in 2 double bonds. They are still both not aromatic structures, and air quotes on the not. But one of them ends up being more reactive than the other. Right? Since there is a difference in their chemistry, we need to name them accordingly. We need to come up with a different way to classify them. And yes, this is not particularly pleasant, but this is the way it works. Cyclobutadiene does not get referred to as not aromatic. I know, there's a lot of knots. Our cyclohexadiene gets referred to as not aromatic. our cyclobutadiene is not aromatic, but it's also not aromatic. Yeah, run that through your head 5 times fast. We'll refer to it as anti-aromatic. Okay. Which actually holds some meaning. Not aromatic, we would expect to react just like a normal double bond. Aromatic means it doesn't react like a double bond, like it doesn't react at all. What is anti-aromatic? We're saying it is the opposite of being aromatic. Well, aromatic was incredibly stable. Anti-aromatic will be not stable. The anti-aromatic nomenclature gives us more information than just saying it's not aromatic. Okay? Not aromatic means we run at a standard double bond. Anti-aromatic means we're running at a higher reactivity than a standard double bond. Okay? So within those rules, and this is where it's fun, aromatic compounds fulfill several criteria, which I've kind of grouped loosely as 2 things. We have a fully conjugated ring with overlapping p orbitals. Okay? A p orbital, which you'll notice I've put in quotes now, can be generated through resonance. This is a tricky thing to watch out for. Okay? They will also meet Huckel's rule. We have an odd number of electron pairs, okay, involved in the pi system. These must be electrons in the pi system. Okay? I don't care about electrons outside it. They have to be inside it. Anti-aromatic compounds will also fulfill 2 criteria. Same rules as aromatic, except we now see an even number of electron pairs. Okay? So we end up with 4n total electrons, as opposed to 4n plus 2. Non-aromatic, invalidate all of the rules listed. Okay? So there's something wrong with the structure that prevents it from having a fully conjugated overlapping p orbitals. Okay? The other thing that can potentially pop up with non-aromatic that you have to watch out for is that it can be referenced as a trick question. Not fun, but it happens. The structure would fit if we looked at it as anti-aromatic, okay, according to our rule set. And for some reason, you look up your answer key and it says it's non-aromatic. Okay? You may wonder, well, why? That seems a bit weird. Well, the compound, I hate drawing this compound. Let me see if I can do it. This compound, aromatic, anti-aromatic, non-aromatic. Do we have a fully conjugated ring? Yes. Do we have overlapping p orbitals? Okay, yes. Huckel's rule, odd number or an even number? Even number. So we would say anti-aromatic. You look this compound up, most textbooks classify it, unfortunately, as non-aromatic, not anti-aromatic. Okay? This is one of those ones that you need to build a model for, and what you end up finding is that this structure is not planar. If it is planar, it fits under anti-aromatic, but what's the issue with anti-aromatic compounds? Why do we choose the term anti-aromatic? They're unstable, they're more reactive. This structure, if you will, has a sense of it being reactive, and so does whatever it can to avoid being anti-aromatic. What does it do? It puckers into kind of like a taco shell. Once it's in a taco shell, do we have overlapping p orbitals? No. So it actually invalidates rule number 1, which makes it non-aromatic, not anti-aromatic. Kind of get it? Not easy to see. Okay. So let's take a look at some examples. I'll give you a couple minutes. Aromatic compounds. Go through and first take a pass and say, are they aromatic? If they are aromatic, go ahead and stick with it. If After you've assigned the ones that are aromatic, go through and try and decide, is it anti-aromatic or non-aromatic for any of the others. Okay? This is something that I would highly encourage you to do quickly, as best as you can first, and then go back. Sure. See if I can do them right. Aromatic, anti-aromatic, non-aromatic, aromatic. Are there any you want to look at in particular? Last two? Okay, we'll definitely take a look at the last two. Anything else? Everybody got every other one right? Fourth one. 1, 2, 3, 4. That one? But you got this one, the one right before it, correct? Okay, so we'll look at 3, 4, and then what is that? 6 and 7? Okay. What happened with that now first one?
They're not fully conjugated.
You have to have a first step is you have to have a fully conjugated ring with overlapping p orbitals. We do have a ring, and we do have some conjugation. Those pi bonds do resonance with each other through that last sigma bond. Can they resonate the other direction? Can I push the electrons up that way? This carbon would have to have a p orbital to accept those pi electrons. Does it? No. It is sp3 hybridized. There is no leftover p orbital, which means I cannot push electrons through that carbon, which means resonance does not happen through that atom, which means not conjugated. We must have a fully conjugated ring. It does not satisfy rule number 1, so it is non-aromatic. What about the next one?
It has that p orbital.
Because we are now sp2 hybridized, we do have an empty p orbital, which means I can do resonance through that position. Okay. So I do satisfy rule 1. I do have a fully conjugated ring with overlapping p orbitals. Now I move on to step 2. I have an even number of pi electrons. That does not satisfy Huckel's rule, so it must be anti-aromatic. Does that cover you? Okay. Last two. What's going on with these guys? What's the hybridization of that oxygen? I've heard two answers here. I heard sp3 and I heard sp2. sp3, why'd you say sp3? 1, 2, 3, 4 groups of electrons? That says sp3, I agree. sp2, why'd you say sp2? Somebody said sp2. Did you say sp2? Oh, well, son of a gun. I guess I said sp2.
Is it because the electrons are inside the ring? Or does that not?
We'll address that comment in a second, too. What is the relationship between these two structures? Resonance. Which one is the correct structure? Both. Fair enough. If both of these are valid, then I have to use both of those to interpret the hybridization of that oxygen. The hybridization of that oxygen in that structure? Now it's sp2. What does that mean? Technically, our hybridization is somewhere between sp2 and sp3. You're welcome. I didn't invent that. Okay. But because it has that sp2 characteristic, we have the ability to pass electrons through it via resonance, which means the electrons that I used on that oxygen, or actually we'll double back to that in a second, that I have a fully conjugated ring. Every single one of those atoms within that ring has at least sp2 characteristics, which means I have a p orbital to pass electrons through. Questions on that? So rule 1 is satisfied. Rule 2, how many pi electrons are involved? Why do you say 6? I mean, there's a lot of confidence in that shout out of a 6. I mean, there's 2 in each of those pi bonds, right? I still have 2 pi bonds here. So you're counting 6. I still only see 4. Why do you count 6? I will also count those 2 as part of the pi system. How do I know those 2 electrons are part of the pi system? Not that it's negatively charged. I can use it as part of my resonance. If I can use it within the resonance, it is now, by definition, part of the pi system. That's why it can resonate. Okay. So I end up counting that lone pair into the system. That is really, really weird. Okay. Particularly because what is the hybridization of that carbon with that negative charge? You just said sp3, really? Is it sp3, that same carbon? It's this weird gray area halfway in between. It's a ninja, sure. sp2.5. Okay. Those electrons can move from an sp3 orbital into a p orbital to facilitate electrons moving through the structure. Why would it do that? If I count those electrons in the pi system, how many pi electrons would I have? I would have 6. And if I have 6 pi electrons, what kind of structure do I have? Aromatic. And what is special about aromatic? Incredibly stable and low energy. Those electrons will shift out of that sp3 orbital and into the pi system because it makes the structure more stable. How much of a change is it really going through? What is the bond angle in an sp3 atom? 109.5. To get them into the pi system, it needs to be 90. We're going from a 109 degree angle to a 90 degree angle. It's really not that much of a shift. Okay. So the structure will adjust to include those pi electrons because that makes it aromatic, which now increases its stability. Okay. Make sense? Or at least as much as you can make heads or tails of that. Okay, so then the last one. Why is that last one aromatic? Lone pairs on what? That top nitrogen will take on some sp2 characteristic so that it can do resonance with the pi system. So those electrons will count towards your pi electrons. But aren't there more pi electrons? Can't I just show this arrow just as easily? Yeah, that arrow looks perfectly legitimate. What's wrong with it? There's an interesting idea. What do you mean less stable?
Because that carbon negative charge
True, but we generated a negative charge with all our other resonance structures.
Well, then more electronegative elements are either positive, while carbon is negative. Doesn't matter.
It's not linear.
What is the hybridization of that nitrogen now? SP. What bond angle do we have? 180. 180 degrees in a, what is that, pentagon? What kind of bond angle do we want in a pentagon? Ooh, not 180. Good answer. Okay. Okay, remember, when we talked about benzene, we didn't want to put two double bonds in a benzene because we couldn't generate that structure, two double bonds next to each other. Okay. We can't generate that hybridization or that effect because it structurally can't make those bond angles fit. Okay. There's another big reason. What is the hybridization of that nitrogen? Okay. So we just said, I'm going to need to use this eraser. That hybridization is sp2 to start. Okay. So it has an empty p orbital. Where is that empty p orbital currently located? In the plane of our paper. So it's coming in and out of the board at you. Where's the lone pair? There's our fancy word. The lone pair is perpendicular. For there to be resonance within the pi system, where's the p orbital on the next carbon need to be? Same plane. And the next one? Where is our lone pair in comparison to our pi system?
Outside of it.
A perpendicular orbital, which means the overlap is not there. There is no orbital overlap between that pi or that lone pair and the rest of the structure. Because of that lack of overlap, it cannot get involved in the resonance or in the pi system. If for some reason we said, screw it, let's just do it. Let's make it part of the pi system. As you rotate those electrons up to put them into the pi system, what happened to the electrons that were already in the pi system? They move out of the pi system. That nitrogen can only contribute one pair of electrons. And it is already involved in that pi bond.
Question about the oxygen one that you're looking for, is that where you were, is that why it was drawn with one pair in and one pair out?
No.
Oh.
I'm going to look at that again in a second too. So when we go through and look at the atoms within our ring, if we have a heteroatom, anything not carbon, anything just not carbon, okay? If it has lone pairs, those lone pairs can contribute to the pi system if they are in a favorable orientation to rotate into the pi system easily. The only way they can rotate into the pi system easily is if they are in an sp3 orbital. Okay? You're moving from 109 to 90 as opposed to a full 90-degree rotation to get it into the pi system. Okay? So if your atom is sp3, you can count one lone pair. A question that Cassie brought up, where did it go? With that oxygen. You made comment that that lone pair was drawn within the ring, and that's why I can say it's aromatic.
I guess that's just an easier way to show it. I know electrons can move around, so it's not.
Is that structure an equal representation? Sorry.
Yes. Well, yes.
Perfectly acceptable way to draw that structure. Why is the lone pair initially drawn inside? Because it's easier to draw it there. That is it. Okay. You can count the lone pair because it is sp3 hybridized. That's how it counts as part of the pi system. Okay? Questions? Okay, because I don't think you're quite broken yet. What do you think on this one? This is what we'll end with. Aromatic, anti-aromatic, non-aromatic. Do we have a fully conjugated ring with p orbitals? Yes. That carbon is sp2 hybridized, which means it does have a p orbital. I do have an overlapping pi system. Okay. Now I have to be concerned about the number of pi electrons involved in this.
Or 4.
Minimally, how many do we have? 4. The double bonds within that ring must count. Then you have the carbon-oxygen double bonds. How many of those electrons can you count to being part of the pi system? What do you mean you can only count one?
One's going to do resonance and the other's going to do it out.
If we look at the electrons in that pi bond, there are 2. One of those electrons came from oxygen. One of them came from carbon. The one with carbon can stick with the carbon and be involved in resonance, which means how many electrons do I have in the pi system? 6, because there's a second pi bond at the bottom. There are 6 pi electrons involved in this structure. This compound, quinoline, I believe, or quinone, is an aromatic compound with 6 pi electrons. And it reacts like a diradical. Why a diradical? The oxygen on the outsides really has an unpaired electron because the electrons from your pi system are involved in resonance through the ring. Tricky little compound. Okay. We'll look at reactivity on Wednesday. We got a couple applications with our aromaticity.
Can you say what that again?